Welcome to the GATE 2021 model courses on control systems. Today's our topic is root locus technique linked with the state space. Let us go to the question number 1. So they are given a state variable model and asking for you to find the root locus diagram as k varying from 0 to infinity. So that are your given options. So from state variable model, how to find the root locus diagram is, first we have to find the characteristic equation. So this is the given state variable model, and the characteristic equation formula is mod of Si minus A equal to 0. Here Si is INT matrix 2 by 2 multiplied with S, and A matrix is this one, equal to 0. What is Si minus A? Is S minus 0, 0 minus 1, 0 minus of minus 2 is 2, S plus K. What is the determinant of 2 by 2 matrix is ABC is AD minus BC. For that is the determinant of this matrix is S square plus Ks plus 2 equal to 0. Now this characteristic equation we have to keep in the standard format of 1 plus G of S equal to 0. In that G of S, in the numerator part only the variable parameter K should be located. What you can write that characteristic equation is 1 plus Ks by S square plus 2. Now compare this characteristic equation with your standard format, that is 1 plus G of S equal to 0 for unity feedback system cases. For non-unity feedback system, it will be 1 plus G of S H of S equal to 0, where that G or GH is your loop or open loop transfer function. What is your G of S is Ks by S square plus 2. So this is your given open loop transfer function. Whenever they give the open loop transfer function, directly seeing that open loop transfer function, we can draw the root loss diagram easily. So the open loop transfer function is Ks by S square plus 2. Now to draw the root loss diagram, first we have to locate all the open loop poles and zeros. We have two open loop poles where they are located is plus or minus j root 2. And we have one open loop pole lying at origin. One open loop 0 lying at origin. So at k equal to 0, what are the closed loop poles? Are nothing but open loop poles. That is plus or minus j root 2. At infinite gain, they are open loop zeros, in which one is lying at origin. One more will be at infinity at an angle of 180 degrees. That is only our asymptotic angle. Or how many asymptotes we have it here is number of open loop poles minus open loop zeros. Number of open loop poles are 2, open loop zeros are 1, therefore 1 asymptote, and angle of asymptote is 180 by number of asymptotes into 1, that is 180 degrees. So one asymptotic angle is 180 degrees. And the way root loss light diagram lies on the real axis, if you select any root between 0 to plus infinity, on the right hand side the number of open loop poles and zeros are nothing, that is 0, which is an even multiple, therefore root loss doesn't lie on the positive real axis. If you select any root between 0 to minus infinity, on the right hand side how many number of open loop poles and zeros we have, it is 2 plus 1, 3 odd multiple. That's why the root loss lies on the real axis between 0 to minus infinity. Let us show that with a different color instead of red color. Just with green color, I am showing the root loss existence on the real axis. Next, we have to find the angle of departure of these poles, which are lying on the j omega axis. How to find the angle of departure of j root 2 is, the mathematical formula is angle of departure is 180 plus phi, where phi is phase angle of open loop transfer function at that pole. That is, I will explain this one with a graphical method easily for you. This is the location of open loop poles and zeros. And here we have to find the angle of departure of this imaginary root. What is phi is measure the angle from all the open loop poles and zeros for that imaginary root from the remaining poles and zeros. That is, what is the angle we'll have from this pole to this imaginary root is, that will be obviously, if we join it, that will be 90 degrees. Since it is a pole which lies in the denominator, we have to take the negative sign, minus 90 degrees. Again, measure the angle from the 0 to this root, which you will get it as also 90 degrees. Therefore, since it is a 0 plus sign, plus 90 degrees. That is phi. What is phi is measure the angle from remaining all the open loop poles and zeros for that imaginary root. For this remaining one pole and 1 0 will make what angle to this imaginary root is 90 degrees. Pole given negative sign since it lies in the denominator part. 0 lies in the numerator part, hence that angle will be giving as positive sign plus 90. Hence, the total angle of departure of the imaginary root, which we'll get it as plus 180 degrees. Then what about the angle of departure of the conjugate imaginary root is, conjugate pair is, it will be just taking negative sign, that is minus 180 degrees. Or 180 degrees means this pole will departure with an angle of plus j root with 180 degrees left side. This one minus 180 also left side like this. So these two poles which will departure with 180 degrees means they'll be in complex nature. Compulsory these roots should break in onto the real axis. That's why hence the root lowers diagram will be in this manner. We can expect it. That is, the angle of departure of this pole is minus 180 degrees. This one is plus 180 degrees, this is minus 180 degrees. For these two poles, compulsory they have to come onto the real axis. Since for k equal to infinite, the two closed loop poles are on the real axis. One is at origin, another one is infinity at an angle of 180 degrees. Therefore, they'll form a perfectly a semicircle. As k increasing, these two poles exactly break in somewhere here between 0 to minus infinity. After breaking, one closed loop pole reaches to this 0 as k tends to infinity. Another one terminates to infinity with an angle of 180 degrees. Hence, the correct answer is option C. Thank you.